Alright, my good friends, let's talk about an electric furnace. Very simple device. Only a few things you have to know, a few things you have to check, right? So, first thing, let's check what kind of voltage we're going to get. Matt, what typical voltage would you have on an electric furnace?
120 or 240?
Well, 240, right? So 240 would be a typical voltage because something that's going to electrically heat is going to require a lot of energy. So for that we need, two phases of 120 volts, so 240 volts total. So first thing I always want to do is make sure we have 240 volts at our power port coming in. Every single time you're going to see a circuit breaker on an electric furnace that's mounted onto the furnace itself, sometimes you're going to see two of them. Typically the second circuit breaker is the one that's a extra power for the second stage. So most furnaces will have two stages. The second circuit breaker doesn't do take any part in controls, blower, or any actions other than it supplies power to another circuit. So back here we had, Paul, where was the electric? Oh, there you go. So this is our electric section. Inside of this, we're going to have three of these. And all you're always going to see is where the power comes in from both sides, because it's 120 on both sides. Now the power is going to always go through a thermal disc, which is this switch. So power comes into here directly. That's one of these legs of 120 volts was going to go to one side, right to the heating element. The other power is going to go, after it gets relayed in, to this thermal switch. If the thermal switch is cool or not overheated, this disc right here stays snapped in and power is able to flow through it and into the other side of the element. So then we complete the circuit between two phases of 120 volts to get our full 220 volt phase. So all that's going to happen is, you guys see this little wire, it's kind of like a radiant heating hose, right, where water flows through. All that happens is, instead of Mr. Aqua, it's Mr. Electron that runs through on both sides. Sergio loves that, Mr. Electron, Mr. Aqua. And what happens is, this wire heats up as it starts to conduct electricity. That's why it's conductive heating, right? It starts to heat up to a point where normally you're going to see this turn orange or red unless the fan is running. Even sometimes with the fan running, if you could still see it, sometimes you can through like a humidifier pad, you're going to see center orange, right? As a matter of fact, if you're running service and you see, and if you're able to see this while it's running, the fan is blowing, and you're starting to see a lot of orange in here, that indicates this is dying. When the fan is going, this should not have a visible color on it. Typically you start seeing orange, red, it's time to recommend replacing the electric element. Because all it's going to do eventually.
If you get a clogged filter?
That's exactly right. Rich is right.
What is it?
So if you have a clogged filter, or if the fan isn't obviously functioning, or if it's set for too low of a speed, or if everyone's covered all the ductwork, right? Someone shut off all the all the supplies, the returns are covered with carpets. Same thing will happen, not enough airflow. And it may not be such a low amount of airflow that it'll trip the thermal switch, but it'll start affecting the way this cable, is heating. So if this starts to overheat, it starts to get crusty. See, my hands are full of dirt. That's not just from working earlier, but you touch this, it starts to get brittle. Once it becomes brittle, it'll eventually snap and needs to be replaced. So as we're starting to do a lot more at 990 and all the other electric heated places, you'll have to start thinking about it. Even though the new furnace we're putting in, 5-10 years from now, we go back to those, let's start noticing this and preemptively replacing it for people before it becomes an issue. Like in that building in 1600 South Indiana, where basically we're doing this all the time right now.
The wires burn too.
Wires, well, typically these wires will surrender first. This is supposed to be a little bit thicker, and this is supposed to surrender. It's supposed to burn before this burns, right? But with ultimately being used, cooling and heating of itself, and if it's not getting enough airflow, this will also burn through. At any point, electric, heating is somewhat dangerous, so you got to make sure everything is nice and tight. You got to make sure everything is, well connected. So, and it's okay to replace it and not have a person worry about it. This burns. This is basic controlled electrical fire. So another thing to make sure is nothing ever falls on top of this. If you have a humidifier, make sure the pad doesn't go in there. Obviously, the humidifiers we put in are fine. A few times I found a piece of plastic fall into it, melts. It doesn't start a fire, but it starts smokes. So this gets really, really hot. Anyway, once you get this thing on, let's turn this thing on. You can see how everything functions and how to determine if it's actually working. Because measuring voltage, I don't have to even dig in here to show you this, but this sits in there, right? If you're gonna measure voltage across here, that doesn't even necessarily mean that it's actually working. The only way to find out, to determine if this is functioning, is to see if it draws amperage. If it's drawing amperage, it's functioning. Also, knowing how much amperage it draws will allow you to determine how much heat you're putting into the house. And you guys probably should remember that from the Watt's law. Remember that?
Ohm's law.
Oh, and Ohm's law, right. So I'm gonna turn the heat on. It's too warm in this place. So now let's see if when the heat comes on, this should instantly fire up our fan. See? The fan's gonna come on. And now I'm gonna switch my meter from voltage to amperage. So right now I'm reading 40 amps, right? You're gonna notice that you're gonna read and I know you're gonna ask me this, it's not 40 times 2. You're gonna read the amperage of the entire circuit, because this is one big circuit. So now as I'm gonna switch to this side, you're gonna see 40.3 amps, the same thing, okay? That's because these two are part of a circuit, You're basically feeding Mr. Electrons from both sides and they're running backwards, right? The Mr. Electron from here is going to run through the heaters, come back, run this way. Mr. Electron from this feed is going to go through a circuit and run back on the opposite leg. That means that you're not adding the amps that you measure on both of these legs, but it's basically whichever one you're going to get, this is what you have, So right now we're drawing 40 amps, and you're going to notice that we have a 60 amp circuit breaker here, right? So typically protection is going to be about 80%. Sorry, the usage is 80% of protection. So if you have a 100 amp circuit breaker, you're going to draw about 80 amps, right? If you're going to have a 60, you're going to draw 30 to 40. So we're drawing 40 amps. So now we know that this is working. I mean, obviously we can check now to make sure we have warm air coming at the top and it's warm. Also, typically, the air discharge on the electric furnace is much cooler than a normal furnace, You're looking to get at most 130 degree discharge of air. Typically 110 is what you're gonna have, Unless you have really, really oversized furnace and not enough ductwork, then you're definitely cooking the wires. Which 110 degrees is enough. When you're bringing in 60 to 70 degree air, you're gonna get a 40 delta T. Electric furnaces take a lot longer to heat up a house. So a normal conventional gas-fired furnace has a delta T or differential temperature of about 80 degrees. So newer ones are maybe closer to 7, They're more efficient. The older ones were always 80, So you can heat up the house much faster than you did. So electric furnaces are actually better for getting heat more equally throughout the house because they take longer to heat up to get the thermostat to reach the setting point. So you actually deliver more quality, well-distributed, heating throughout the house. You know what I mean? So, good. One more thing also to remember, 2 things that you're going to look for is always a thermal disc, right? If you guys look inside there, you're going to see 3 separate thermal discs, right? Each one of them is going to be like this, and each one in the back of it has this snap disc. If you want, just come feel it, This snap disc, it literally pops in and out. You can hear it. So when it overheats, it basically pops itself in, and then see, feel that, right? You see that? You actually feel it. So that's what happens, It's good. Pass this thing around, brothers. So those you see, they're sitting there inside the airflow, and the back is where it reads the temperature. Every one of these elements is going to be controlled by a sequencer. Sequencers In this case, these are electronic controllers right there, if you look inside. Some older furnaces will have a thermal sequencer, where there's a little piece of wax that heats up once it gets electricity going through it. That's how that works. There's wax inside these things, yeah. Wax or oil. All of us had oil, new ones are wax. Kind of like, Tommy, if you think of Uponor controls for water flow, some of those have wax also. They get 24 volts, and the wax is what warms up and opens up the valve to allow the water to go through. So, you know, a lot of things actually are pretty well. Wax is the good, you know, same control to like warm up and cool off. It doesn't dissipate when it's sealed. Anyway, so if you look inside, you're gonna see two of these sequencers. That's because one of them is for the double, which is your main heat, and the second one is like a W2, and we don't have that connected because that would be its own separate circuit breaker for the second heat or the auxiliary heat. Most of the time, sometimes you're going to see even three on your control board. You're going to see S1, S2, S3. So S is for stage of heat. You know, typically stage 1 is going to be like your W, right? WS1, and you're going to see that a lot on the Unica control boards. And then W2 is also S2, and S3 is a separate circuit. S3 is typically connected to an emergency output on your thermostat. So some thermostats, especially for heat pumps, will have E for emergency. That is typically what you connect to a separate or auxiliary electric strip inside of an electric furnace. It's the same thing for Unico. Unico has the same thing. It's got 3 controllers, and one of them has S3 will connect to the emergency heat. That's something that, not to get off topic, but all those heat pump thermostats, when you have emergency heat, that it really means you turn it on other than everything else in your heat pump or other source of heat. It literally knows that it's in emergency, so everything else is broken down, It could be used for that, or it could be used as a second stage, as W2. So you decide as the installer who connects the low voltage end of it to see if you're connecting it as a W1, W2, W1 being the main circuits that come like the 2, and then W2 is the second stage, or if you want to use the second stage as E for emergency and a thermostat. Now this is not connected to a heat pump, obviously, but it could be connected to a heat pump, in which case the heat pump would be like a primary source of heating, and then your electric heat would become in use in case the heat pump isn't capable of heating up, or in case it's in a defrost. Go.
Could they both run at the same time?
Yes, great question. In this case, you can use both the heat pump and electric heat at the same time. And the reason for that is the coil is below the blower and the electric heat section is above the blower. Meaning you're not going to overheat the coil and cause a problem for the outdoor unit because you're not throwing heat up to it. When we do those gas furnaces combined with the heat pump, or Peter calls them dual fuel applications, that's when we cannot run them at the same time because the source of heat is on the bottom and then the coil sits on top of the furnace. So if you turn both of them at the same time, you'd be running really hot air across the then on the heat pump application condenser coil, right? Normally evaporator coil, but in the heat pump that becomes a condenser coil. That would overheat the condenser. Typically, you would start getting pressures of 700 to 800 if the heat pump was able to run. Now, most modern heat pumps will sense the high temperature of the liquid and turn themselves off, right? As an emergency, but older heat pumps didn't have it. Either way, it won't function. That's why, we go through the whole setup on our thermostats on EcoBeast to make sure that only one can run at the same time. But when you have electric furnace or you have a Unico with the electric section in the front, you can run both the heat pump and the electric section at the same time because the coil is behind the blower and electric heat is on the other side of the blower. Do you understand?
No.
So this is very important to understand, When the heat pump heats up, this is the part that gets hot, right? And you run refrigerant through it at X temperatures. Because this is basically, you reverse the flow of refrigerant, this becomes a condenser. This is the part that discharges the heat. Now, in here you have cool air from the house getting sucked into this coil, right?
Yeah.
And then the electric heating part sits above it. So this part doesn't affect the coil. But if you have a standard furnace, it's reversed, right? The coil sits on top of the furnace.
Yep.
So then the heat from the gas-fired furnace will be affecting the coil, right? And we don't want that because the refrigerant going through is already hot. And we cannot take superheating it even more. Do you understand now?
Yeah, makes more sense.
Because if you guys, if I'm talking and, you know, I know some of you guys this is easy, for some guys, you know, you have no idea what, you know, the details of it, don't hesitate to ask, you know. Want to make, go ahead, Johnny.
Why do those two models exist?
Which one? Why is it set up
the
like
two
that?
different versions that you're talking about.
Okay, that's, you know, that's function of what's out there, right? So gas-fired furnaces have been out there for such a long time, and traditionally no one cared about attaching heat pumps to them. Now there is a way to actually to install a furnace and be able to use it in the same way, but you have to do something that's not traditional. You have to put the evaporator coil under the furnace. Majority of the time, when you walk in people's homes like your house, you have the furnace and then the evaporator coil or the air conditioning section, heat exchanger sits on top of it. We could potentially reverse it and put the coil on the bottom and suck through the coil. There's no reason not to. It's set up the same way for us to suck through it as for us to blow through it, but we traditionally don't do it. And actually, as a matter of fact, Peter, next dual fuel job we're going to sell, we're going to install a coil on the return.
All right, perfect.
I know
Matt was
it's
the, Matt's cousin.
Coil on the return?
Yeah.
Yeah.
We're going to install it on the return, and we're going to put the
Where's the
furnace on
filter?
top of it. And we're going to, it's got to be underneath the coil. Because you got to protect the coil. So it's the same as you, that still remains the same. Now, I've done this before on air conditioning systems. I forget what the reason was, but there was a reason why I did it like that. Probably because it was easier, you know?
Sometimes on horizontals you do it there, right?
On horizontals, you do it all the time. You're right. We flip reverse, suck through it, or blow through it, you know? The only difference is you have to make sure you have a trap on the drain effectively. It's the same thing, you know? It doesn't make a difference, but we got to try new things, right? So, and if we do that, then we can certainly operate it like that, you know? We can operate it as a heat pump working together with a furnace, you know? But, you know, this is, you know, generally speaking about electric furnaces, that's what we're going to run
How
into.
do we know what kilowatt this is?
How do we know what kilowatt this is? It's a great question. We can figure it out ourselves.
Okay, this should be 8,000 then.
Well, let's do the numbers, right? So we know how much it draws, right?
40.
Well, I don't know, what was the voltage, the original
Oh,
voltage?
it's 135 volts. Eric, get a calculator out. You know?
It's 240 volts or 2?
It was 230. Let's be exact. It was 235 on the voltage
Oh, okay.
times 40.3.
Why 40.3?
That's
That's
our
gonna give you the
average.
wattage.
9,470.5.
No.
Say that again.
9,470.5.
Okay, so that means 9.4 kW, 9.4 kilowatts. So that's the actual heating output of this unit.
So is that a 10K or 8K?
So that's a 10 kW. Typically, they're going to be a little bit lower than they say they're rated for. That's because they're rated for higher voltage. So when they rate these units, they rate them at like 240, 248 volts. So
Do we run
not
into-
always
do we
realistic
run
to
into
have.
these at 208?
What's that?
Do we run into these at 208?
If we,
voltage?
Eric, whip out the calculator. Let's go again. We're going to find out how much heat we're going to get this if we're sitting in a 208 high rise.
Less.
Less, yeah. Let's see exactly. So go
Quite a
40.3
bit less.
times 208.
Let's say about
Quite a bit.
7,000.
20% less. I'd say 7 to 8,000.
That's a 7.
Yeah, 8.3.
8.3. So it was one. So we lost a kilowatt. So kilowatt's a lot. So now, Eric, just so you guys remember, roughly, you know, each kilowatt is 3,500 BTUs. It's rough. Okay, so 3,500 BTUs equals a kilowatt. So now, what is the number that we had before? Not the one I just told you.
9.4.
You go 9.4 times 3,500.
32,900.
Okay, so that means this furnace is outputting 32,000 BTUs. And remember, with electric heat, it's 100% efficient. Conductive electric heat is 100% efficient. There is no loss for burning, for exhaust. So this is literally the BTUs that are going into your space. So this furnace, at this moment, is capable of adding 35 or what was that? 32,000 BTUs. So just remember those. The good numbers to remember are this: voltage times amperage equals wattage. So that's how you get the kilowatts. That's the that's the power achieved. And then to know how much BTUs, then kWs times 3,500 is your actual BTUs. So BTUs are important because that's how we know how much heat we get for something, And Eric, do you remember what's a rough idea of how many BTUs do we need per square foot to heat up a house in Chicago?
Windows,
Do you remember that?
windows insulation.
Square foot.
Yeah. No, how many BTUs are needed per square foot to heat up our home?
500.
40.
If it's an older house, yeah.
So older home,
older
like
house.
the older home for 40. If it's a super tight house, it's actually 20. Newer house built after 1990 is supposed to be 30. But if you go 40, you're never going to be wrong. Just because sometimes it gets colder. So having said that, this being a 32,000 BTU, so go 32,000 and divide it by 40. And let's see how many square feet of the home we can achieve with this setup that we have.
658.
So 650 square feet. So
Like
that's a
a
small
front
apartment.
office.
Small
Yeah.
apartment. So small apartment is all we could really do. And that's all we can do. So that's about it. Do you guys have any questions?
I have a question about
Yes, sir.
the breaker. You said something about like, let's say the breaker is 40 amps. It's usually, whatever the load is, it's usually 80%.
Okay. Yeah. So the actual power draw or the current is the word. That's amperage. The current draw is going to be 80%, about 80% of the circuit breaker. The circuit breaker is protection of wire. Just remember this. The function of a circuit breaker, the only function is to protect the wire. Okay? Or protect the, yeah.
If it's drawing too much current and the wire's too thin and it's low red hot.
Correct.
Yeah.
Either the circuit breaker breaks or the wire burns. There are only two possible things when you have over amperage, when you overdraw the power, right? So the circuit breaker is going to always be bigger than what you're actually drawing. If you're going to start drawing power close to, like, if this is 60 amp and you're drawing 55, 56, at some point this is going to start tripping all the time. That means there is a problem with this. Okay?
Especially with older motors. This is an ECM motor, but I mean,
Right.
it's easy start, but the other one's surge.
Correct. So, and that's on any electrical equipment. If you're going to start tripping circuit breakers, that means you're drawing too much power. There's a problem with machinery. The motor's older. These are getting weaker. The electric strips. Compressor is overloaded. That's why it trips. You get it? These are Isaac. Yeah.
Sorry, I'm writing down.
There's no problem. You understand?
Yes, yes.
Who are you texting? Sexy ladies?
My future thought.
Nice.
What's called?
No worries.
Okay.
Right? Okay, sequence of operations. So 24 volts from the transformer goes to the control board. The control board will send 24 volts to the R terminal on the thermostat. When there's a call for heat, the thermostat will send power to both the G, or the call for a fan, and W to turn on the electric heat. Once that happens, the 24 volts in here will engage two separate relays. Whether those relays are inside the control board or actual relays, same thing will happen. You're going to send 240 volts to the blower motor to engage the blower motor, and you're going to send a 24 volt signal to close the sequencer or the relay that's going to take one of these legs and complete the 240 volt circuit into the electric heating section. And that's pretty much the end of the sequence. So there's not a lot of things happening, Once you have the thermostat calling for heat, you're engaging two relays. Those relays are either external or internal to the control board.
For electric heat, usually it's a contactor, just like on a condenser, it just closes the 24 volts and just like turning on the condenser outside, except it's on a W.
Yeah, except for it's, as a contactors are loud and chattery, so for the most, and Tom is right, some of the external electric heaters will literally have contactors. And people complain they're loud because they make the chattering sound. You're gonna hear that every time your heat comes on. So Those are much softer, nicer relays. The one with a time delay inside, or old school traditional sequencers that work on temperature. They warm up to close, like we talked about before. And the reason you would have an old school heater that would have multiple electric strips together, you would have sequencers don't get engaged at the same time. If you have 3 of these heaters and you want to bring them all at the same time, you really don't want to do that. You're gonna, most of the time you could trip the circuit breaker. You can have nuisance trips. So the first stage will engage, and that part will start warming up the sequencer. Then the sequencer turns on second, and it starts to warm up with 24 volts, a third sequencer, and they're spaced about 2 to 3 minutes apart. So then you turn up all your strips within like a 9-minute time frame. You know, you do that so you don't trip the circuit breakers needlessly. That's the only reason, you know. This probably can actually do that inside the computer control board. So electrically, furnaces these things are very easy, you know. As long as you remember that the information you're gonna get is using an amp clamp. Remember that. You cannot diagnose an electric furnace without an amp clamp. Knowing voltage where it goes isn't gonna be enough. You're blind. You don't know where it's drawing, you know. You don't know how much it's taking, you know. This will tell us, you know how much is going in there, what BTUs we're getting. Is that what it's supposed to be? You know, if it's like, you know, we just figured out that this is a, 10 kW system, right? So 10 kW system, we were able to actually measure how much, how much wattage was being used. And that's how we would get to that.
You'll say it on the nameplate somewhere?
It'll say it on the nameplate. It'll say it always on the electric strip, because this furnace is going to come with options. You don't always have to put in a 10 kW. Like Unico systems, you know, we can put it, you know, some of them, the bigger ones, you go up to 25 kW, you know, but you can go as low as 5.
Yeah,
So-
they range from 5 to 20 non-standard air handlers.
So don't try to read on the model number of the equipment. That's
marked.
unless someone wrote it.
Unless it's factory installed, and
Right.
they will denote on the data plate, if it is, there'll be an X next to the kilowatt electric heat kit that is installed.
All right, guys, I think next section is I want so Rich and Eric, Sam too a little bit, mostly was Rich and Eric and me. They installed a control system over for a Unico that Rich and Georgie did, and they wired it up. So I want you two guys, in your own words, to explain what you did. Always check a single wire. See, I'm getting about 40 amps. If I put them together, I'm getting nothing. That's because we're reading opposite, you know, because they're both working into the different direction. That's why you're reading 0.
Plus and minus.
1.
Is it the same sequence of operation with the heat pump?
No, completely different. But let's not muddy the waters today, because we can go over a different time, because there'll be too much. See, part of our classes I really want to focus on is specific information, like 5 or 10 points at best. Because I think in the past, when we did classes with Derek, there was too much information and nobody remembered anything. That's what I noticed, you know. So I wanna do this where we spend no more than 30, 45 minutes and actually remember something. So if all you guys remember from this is you need an amp meter, you check against amps times volts are watts, and watts, kilowatts times 3,500 are BTUs. I'm gonna write this shit on the wall today, so tomorrow we come back to work, we can double check it. Like I'm gonna start doing that too, like points, because when I do this, I have some points I want to give you guys. It's usually 4 or 5 points that if you remember those were gonna help you, or maybe save you one day if you're doing something tough, you know. So we'll do that. Now let's go. I really want. We're gonna also do something from now on too. Every time we have a class, one of us, not you guys specifically, one of us will talk about a specific job that we did. Because something that we did that was interesting, that was different, so we can all learn from this. So don't be shy. Say what you think. Don't be dicks to the guys who are talking, so everyone can help each other out. Okay? Let's go.
All right, question.